We have been talking about angle bisectors lately. So today I want to introduce another interesting configuration, which is if you draw the circumcircle of the triangle. All right, so you have triangle ABC inscribed inside the circle, and you draw angle bisector AD. All right, so this angle equals this angle, and it meets the circle at point D. All right. So right off the bat, you have this equal this, which means that this is an isosceles triangle. And the reason is simple. In theory, these two chords, BD and CD, they both face the same angle. They're facing the same inscribed angle. So these two chords must equal. Also, if you try to do a little bit of angle chasing, and you will see these four angles, they are all the same. All right, and the reason is simple. For example, now this one equals this because they're both facing the arc BD, right? They're both inscribed angle of BD. And then this one equals this because they're both inscribed angles of arc CD, right? All right, now isosceles triangle is there, but also there are two pairs of similar triangles which are not quite obvious. Let's think about the first one. The first one is this. I claim that this triangle is similar to this one. All right, because, well, to prove a pair of similar triangles, you just need to, for example, find two pairs of equal angles. Right now, I see this one equal this, right? That's angle bisector. Huh? And also this one, this angle here equal this one, because they're both inscribed angle of arc AC, right? So we have triangle ABE. ABE is similar to triangle ADC. ADC, okay? Right? Well, think about a similar pair because symmetrically you have this ABE. Then what about the ACE? You know, you start to think, shouldn't there be something similar to it as well? Yes. Yes. So ACE, this triangle, is similar to triangle ADB, this one. And the proof is very simple, very similar. This angle equal this, right? Angle bisector. And then this angle equal this because they're both the inscribed angle of arc AB, okay? Facing this arc, right? So we have triangle ABD similar to triangle AEC, okay? Right? Now, having similar triangles not only indicates something about angles, but also something to do with ratios of the size of the triangles. Let's see a very direct application, which is this. I found this formula to be very useful, okay? Pay some attention. AB times AC equals AE times AD. Why? For example, think about this triangle. I have AE over AB equal, this triangle supposedly is similar to this one. So AE over AB is supposedly equal AC over AD. Right, so now you have AB times AC equal AE times AD, okay? Very nice formula. It opens the possibility to calculate some more segments when you have a circumcircle in the graph. And what do I mean? For example, in the past, we were able to calculate, if I tell you this is B, this is C, there's three sides of the triangle, this is A, you can calculate AE, right? The angle bisector length formula. Now, not only that, I could calculate this one now. I could calculate AD. Why? Because, well, AB times AC is AE times AD, right? Once you have AE, then you can calculate AD, right? Not a problem, which means you can calculate DE as well, right? Let's see example, okay? Let's check this out. So triangle ABC, the same configuration. Angle bisector A meets the circumcircle at D, meets the BC at E. If this is 6, this is 4, AD is 8. Find DE. Find BC, okay. All right, if I suppose that if you're watching this video right now, you should pause right here, freeze, pause, and think about this problem, all right? All right, now, how do we solve this? Let's apply our little formula now. AB times AC equal AE times AD, okay? So, all right, so this is 6 times 4 equal AE, I don't know what's AE, times AD, I know what's AD, that's 8. All right, so AE equals 3. And so ED equal 5. So I have 3, 5 here. That was fast, no? Find BC. How do we find BC? Different ideas could apply here, but let me show you one idea. If I would think about the angle bisector ratios, we have BE over EC equal AB over AC, which is 6 over 4, which is 3 over 2, right? So I can say this is 3x, this is 2x, what do you see now in the graph? If you take a look at this point, power of point E, 3 times 5 equal 3x times 2x, 6x squared. So x squared equal 5 over 2. X equal square root of 10 over 2. BC is 5x, right? It's 5 over 2 times square root of 10, right? All right, so if you think about power of a point at point E, seems to be quite straightforward. Now, I suppose there are other methods. How about, well, I know AE, right? AE is angle bisector, AE squared, right? We have a little formula here. AE squared is 9, and it's supposedly equal to AB times AC minus BE times CE, right? So that is 24 minus BE times CE, it's again 6x squared. So this equals this. So 6x squared equal 24 minus 9 should go 15x equal to, sorry, x squared equal to 5 over 2. And that was what we had before. And the rest, I guess, is the same, right? You can solve for x, and then BC is 5x. All right. I hope that you have learned something here. All right. Very nice little formulas. Now let's think about a second example here. 2004 AMC 10 B Problem 24. All right, it does not have a graph. I guess the first thing is we should do is draw a graph, right? Now, again, if you're watching this live, you can pause it, freeze it, and think about this problem, all right? And come back, look at my solution later. Give yourself a couple of minutes. So let me draw this graph in the meantime. This circumcircle triangle ABC, AB is 7, AC is 8, this is 9. Point D is on the circumcircle, so that AD bisects BAC. Okay, AD. This is exactly what we're talking about today. Okay, good. Right here. Find the value of AD over CD. AD over CD. Guess what? This triangle. You're probably asking me, hey, why do you think about this triangle? Well, because AD is in this AD over CD, right? When I see AD over CD, I immediately think about this triangle because, well, that's the two legs of this triangle, right? And this triangle is similar to what? Which one? This one. Call this point E, okay? So AD over CD equal AB over BE, which is then 7 over BE. Well, you know how to solve BE, right? BE is like 9 BC, cut into 7 and 8, 15 portions, and you're taking the 7 part, okay? Right? The ratios. That is, guess that's 15 over 9, 5 over 3. Is it here? Yeah, it's here. Good. It's B. All right, very nice little results. So let's take a quick review of what we have learned today. First, you have the circle, triangle inscribed in there, and you draw angle bisector. You have isosceles triangle right here. Okay, isosceles triangle. And then you got 2 pairs of similar triangles, right? ABE is similar to ADC. ABE similar to ADC. And due to symmetry, you have AEC similar to ABD. Okay. Now, it takes a lot of time to practice and to get familiar with these configurations. All right, so that you can realize and you can apply these results on your own, on the run, whenever you need it. It's different to being able to read a solution that I write to being able to solve a problem on your own. They are quite two different things. It takes a lot of time to practice to be able to use them whenever you need it. All right. Okay. So what's the last thing that we talked about today? It was this thing, this formula: AB times AC equal AE times AD. All right. Due to the 2 pairs of similar triangles. All right. Okay. I hope these are helpful for you. And if you like what you're seeing, please don't forget to subscribe to our channel here. All right, and I will see you next time. Thank you.